Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into introducing the topic of probability. Probability is the sort of next major portion of our course following sort of our investigation of correlation and regression and conditional analysis. Both correlation and regression and conditional analysis were attempts to understand the relationships between variables. Probability is really sort of a different ballgame altogether. Probability is really truly sort of its own branch of mathematics. We're only going to do a very sort of quick sort of survey of some major ideas in probability, and we're doing this for sort of two major reasons. One, understanding sort of probability and studying chance and randomness and those types of things is definitely sort of just useful in everyday life, since we encounter sort of, asking ourselves questions like how likely is it that something is going to happen, or how unlikely is it that something's going to happen. Those are just sort of natural questions that arise. And in terms of our course, we sort of need probability as a mechanism for the second half of our class, which is all about inferential statistics. So probability is sort of one of the main tools that we need for that. So we need to sort of do it a little bit of its development of probability just so that we have it as a mechanism later on. So this is going to be our introduction to probability. And we're going to start with a couple motivating examples, sort of showing you guys that your intuition about probability really matches up with the mathematics of probability. So our first motivating example here, right, this guy right here, we're going to suppose that you flip a fair coin once. So you take a coin and you flip it, right? And we want to ask ourselves, what is the chance that you get heads? So pretty much uniformly, when you hear a question like this, everyone answers sort of the same way. They say something like 50% or 1 out of 2 or something along those lines. And even if you haven't ever formally studied probability, everybody sort of gives those answers. And those answers are absolutely correct. So how do we sort of know that that's the case here? And how do we actually sort of write that out in a way that sort of makes sense to people? Well, first of all, some notation. When we want to talk about like the chance or the probability of something, we're going to sort of use this notation. We're going to write a capital P, and then we're going to put parentheses around the thing that we're talking about. So in this case, we'd say the probability of heads. That's going to be our notation. So when you guys see that, this capital P means you're calculating the probability of, and then whatever is in here. So this would be read as the probability of heads. If you remember from algebra classes, this is a very similar notation to like function notation, where you're sort of putting the input, or in this case, the thing you're looking at, inside those parentheses, and then that capital P just represents we're trying to calculate the probability of it. When you go to write a probability, you can write it in a lot of different ways. You can write it as a fraction. In this case, we would say 1 out of 2. You can also write it as a decimal, so like 0.5. Or you could even write it as a percentage, so 50%. And any of these sort of formats is an appropriate way to report the chance or probability, right? Sometimes people prefer the sort of fraction form, sometimes people prefer the decimal, sometimes people prefer the percentage. It's really all equivalent here. But maybe more important is, how do we all know, or why do we all agree that this probability is going to be 1/2, even though we've never really formally defined probability or talked mathematically about how you're calculating that? So where does this 1/2 sort of come from? Well, we sort of know that it comes from the idea that when you flip a coin, there are only two possible things, right? You're either going to get heads or you're going to get tails. So there's only two possibilities, and that sort of tells us about our denominator. Then we sort of say, okay, well, how many ways do we get what we want? How many ways do we actually get heads? Well, there's only one way that you get heads. You get that heads. So there's only one out of two different things that can happen that sort of give you what you want. So we call that 1 out of 2, which we know mathematically is the same as 0.5, which is the same as 50%. Now, there is something sort of subtle that maybe we don't initially think about that goes into that analysis. Right now, all we've sort of said is that a coin has two things that can happen, heads or tails, and heads is one of them, so it's 1 out of 2. But let's think for a moment about like a situation where you go to your car, you take your keys, and you put the keys in the car, and you try to start the car by turning it in the ignition. Now, technically, there's two things that can happen there, right? Your car can start, or your car might not start. But we know that when you go to put those keys in the car, the chance that your car starts is not 50%. even though its starting is only one of the two possible outcomes. So why is it that with a coin, it's 1 out of 2, but with like starting your car, we don't assume that every time you turn that key, you've got a 50-50 chance of starting your car? Well, the reason is that the sort of behind the scenes component is that when we flip a coin, we sort of know that heads and tails are equally likely, right? That the heads and tails side of it are basically have the same chance of showing up, which is why we're able to calculate this as 1 out of 2. Whereas when you start your car, even though there's two outcomes, the car starts, car doesn't start, we know that those are not equally likely outcomes. So the big thing to sort of think about in this motivating example is that probabilities have a natural relation to sort of fractions. We sort of can see that this idea is sort of there's one way we get what we want out of two total things that can happen, but there's also a background assumption that this works well when everything is equally likely. And we'll develop that a little bit in just a moment when we get to our sort of formal definition. But before we do that, let's look at one more sort of motivating example. All right, so now we're going to do another thing that's very standard sort of probability, right? Coins are a classic example of probability because when you flip a coin, you don't know what's going to happen. Same thing when you roll a dice. So let's suppose you roll a fair 6-sided dice and you roll it once. We want to know what is the chance you get a 5 or higher. So what we want to try to do here is we want to calculate that we get the probability of 5 or higher. Okay, so notice again our notation, put that capital P and then write what we're trying to get, 5 or higher. So what would this be here? Well, we want to think about it as sort of a fraction. When you roll that dice, it's got 6 sides, so there's 6 different sort of outcomes that we'd expect, 1, 2, 3, 4, 5, and 6. So it's going to be out of 6. How many give us sort of what we want? Well, we want to get a 5 or higher, so that means a 5 will do it or a 6 will do it. So there's 2 things that sort of give us what we want. So that we would say that the probability of getting a 5 or higher is 2 out of 6. Now, you could have of course, like reduce this as a fraction and call it something else. But if you think about it, if you reduce this as a fraction and call it 1/3, it doesn't really tell us as much, right? This 2 out of 6 is actually a better presentation because it reminds somebody, oh, there's 2 things that are 5 or higher out of 6 total possibilities. You could, of course, though, write it as a decimal if you like. As a decimal, this is approximately 0.333, which would then be 33.3%. All right. So, same idea here, right? Just like with the coin, we sort of relied on the idea that with a dice, every side, 1, 2, 3, 4, 5, and 6, are all equally likely. And then we knew that there were 2 things that gave us what we wanted out of 6 possibilities. So let's sort of formally put something in place, right? Give a little bit of terminology, right, with these things and sort of think about how we can sort of join these 2 examples together so we don't have to rely entirely on just sort of our intuition here. So we're going to give some basic definitions. So, basic definitions. The first thing we're going to define is this concept of what's called the sample space. The sample space of a probabilities experiment is just a list of every possible outcome of that probability experiment. So, real quick, let's go back to those examples and think about what the sample space was in each case. So we'll just go back a little bit. So in this first one, where we flipped that coin once, what was the sample space? Well, the sample space were all the possible outcomes. Well, it would be heads or tails. The sample space here was very simple. There were only 2 possible things that could happen. We could get heads, we could get tails. Let's talk about the sample space here, right? The sample space in this case was a little bit more complex. We were rolling this dice once, so what are all the things that could happen? Well, we could get a 1, 2, 3, 4, 5, or 6. There were 6 different things in the sample space because any one of those numbers was sort of possible. All right, so that gives you guys an idea of what this thing is, the sample space is. It's just a list of everything that could happen. The next term we're going to define is what's called an event. An event is just a collection of outcomes that we're interested in or that we're studying. So if we go back to our sort of examples, the events were these things here. This was the sort of event that we were interested in, the event of getting heads on that one flip of a coin. And this guy right here was the event that we were interested in. The event of getting a 5 or higher when we rolled that dice once. So notice that the event is just the sort of fancy word we use for the thing that we're interested in a particular probability experiment. All right, a little bit of notation. Just remember, when we write this sort of notation, we write P of whatever the event is, and that just means the probability of that event E. All right, we are now ready to formally state the formula that we were using to calculate the basic probabilities in those situations. This is the basic formula for probability. We're going to be using it quite a bit at the beginning. It does have a major limitation. So what it says is that it says if all the outcomes in the sample space are equally likely, then the way you calculate the probability of an event is you count the number of outcomes in that event and you divide by the number of outcomes in the sample space. So this says that as long as all the outcomes are equally likely, then all you need to do to calculate a probability is count the number of ways your event can happen and divide by the total number of things that can happen. So let's just go back and make sure that our formula applied in both situations. So back here, right? If we think about it, our sample space was heads and tails. We knew that those were equally likely. So we'll just make a little note, equally likely, check. And then how did we do our calculation? Well, we said we wanted to get heads. There was only one way to get heads, so it was one way to get our event. And then the number of outcomes in our sample space were 2, so it was 1 out of 2. So our formula, even though we didn't know it at the time, really is what we sort of intuitively did in that first example. Let's look at motivating example 2 here, right? Well, everything equally likely, all 6 of those things. Well, they're all just 6 sides of the dice, so they're all equally likely. So we can give ourselves our little check mark there. Equally likely, check. All right, we wanted the event of 5 or higher. How many ways were there to get a 5 or higher? Well, there was 5 and 6, so there were 2 ways. And how many total outcomes were there in the sample space? Well, there were 6 total outcomes, so 2 out of 6. So again, what this is sort of trying to tell you guys is that, yes, there is sort of a formula for calculating basic probability, but that formula directly matches what people intuitively think about, or what you guys sort of already know about how likely something is to happen. All right, so we've got these basic definitions here. Again, the main things you should take away from this is the sample space, list of every possible outcome. The event is just the name for what we're actually studying, and this basic formula for probability that has one limitation. The outcomes in the sample space must be equally likely. Much later on in our discussion of probability, we'll get away from that sort of assumption and be able to calculate probabilities in a lot of different ways, but for right now, this is our main way of dealing with it. All right, let's look at some other examples then here. All right, so our next example, we're going to go a little bit sort of extending the first motivating example. We're going to suppose you now flip 2 fair coins. We're going to write out the sample space. We're going to try to figure out everything that could possibly happen, and we're going to calculate the probability that you get at least 1 tails. So let's think about what the sample space would sort of look like here. So what does the sample space look like? Well, we've got to try to sort of make a list of everything that can happen on those 2 coins. So we can sort of just write that out sort of visually. What are some things that could happen? Well, you could get heads and then heads, right? The first coin is heads, the second coin is heads. You could also get like heads and then tails. So first one is heads, second one is tails. You could also get tails and heads, and you could also get tails and tails. So in other words, there is our sample space, right? You could get heads and then tails, or you could start with tails and then get heads. You could start with tails and then get tails. There's 4 things in that sample space. Are these guys all equally likely? Well, for sure, right? Because they each just talk about one thing happening on each coin, so they're all equally likely here. All right, let's try to calculate this probability that we wanted in B. So we want to get the probability of at least 1 tails. Okay, well, let's think about this as a fraction. Actually, easier to always think about the denominator first. What's going to go down here? Well, whatever the size of the sample space is, which in this case is going to be 4. All right, now we want to think about our event. We want to get at least 1 tails. Well, this guy gives you 2 heads, so there's not at least 1 tails there, so we don't want to count that. This guy has a tail, this guy has a tail, and this guy actually has 2 tails, which definitely satisfies at least 1. So these 3 would do what we want. So our probability here would be 3 out of 4. which of course we could write as 0.75, or we could say is 75%. So when you go through the process of flipping two fair coins, the chance that you get at least one tail is 3 out of 4, or 75%. All right, not too bad there. Now, the thing I do want to sort of make as a note here, just to make sure you guys sort of see why we took the time to write this out, right? We should just make a note. We could have said the sample space was 0 tails, 1 tail, 2 tails. Right? We could have said, okay, instead of describing exactly what happens on the coin, since we were interested in tails, maybe we could have said the sample space is I flip 2 coins, I get 0 tails, 1 tail, or 2 tails. Those are the only 3 things. But notice that these 3 would not have this special characteristic, that they are equally likely. This guy in the middle, 1 tail, actually is more likely than the other 2, because this guy can happen in 2 different ways, right? 0 tails only happens with heads, heads, and 2 tails only happens with tails, tails. But 1 tail happens with heads, tails, or tails, heads. So these guys are not equally likely. And this is a big concern. We don't really like thinking about the sample space in this way because they're not equally likely, which means we can't use that formula that we developed. So we really like sample spaces like this, where everything is sort of as reduced or as basic as possible, because that has a better chance of being equally likely. All right, let's go ahead, extend this one step further by talking about what happens if you have like 3 coins. So now in this next example, we're going to suppose you flip 3 fair coins. So again, we want to try to write out the sample space, and we want to calculate the probability you get all tails. So let's think about this sample space first. So for A, we're talking about the sample space. Let's see if we can sort of guess how big that sample space should be. Well, if we go way back, right? I mean, we probably don't need to go all the way back to see it, but remember that when we had 1 coin, right? When we just had a single coin, the sample space had 2 things in it, heads or tails. Then we just did an example where we had 2 coins and the sample space had 4 things in it. So now we have 3 coins. And we should be sort of thinking, there's sort of 2 numbers that would make sense for the size of the sample space. If you have a pattern that goes 2, 4, and then the next number, you're probably thinking it should either go 2, 4, 6, or it's going 2, 4, 8. It's either adding 2 each time or multiplying 2 each time. The reason I bring this up is because, as you guys will see, multiplication is one of the sort of key operations when working with probability. There will actually, since there are 3 fair coins here, there's going to be 8 different possibilities. Let's see what they look like. So if we were actually to write these out, they could be heads, heads, heads. Then, of course, you could also have heads, heads, tails. Then you could have heads, tails, heads. You could have heads, tails, tails. Then you could have tails, heads, heads. Then you could have tails, heads, tails. You could have tails, tails, heads. Or you could have tails, tails, tails. There are 8 different things here. Now you'll notice that I sort of organized them in a weird way. The way I organized them is that I sort of broke it down by what happens on the first 2. Notice that in my each sort of row here, I put where the first 2 coins are the same. Heads, heads, and heads, heads. And then we're sort of saying the third coin could either be heads or tails. Then we're saying, okay, what if the first 2 are heads and tails? And then it could either be heads or it could be tails. So I've sort of organized it by putting the first 2 together and then saying the third one could be either outcome. And that hopefully shows you guys why we're getting 8 total things there. You can also just mess around and think about there's really nothing else that could possibly happen, right? You can't think of another combination of H's and T's that I didn't write out here. These guys, once again, are all equally likely. Okay, let's go ahead and then calculate the probability. We wanted to get the probability, we get all tails. Okay, well, first let's think, we know that this is going to be a fraction here. Let's think about our denominator. That's going to be the size of our sample space. So we had this sample space that's got 8 different things in it. So it's going to be something out of 8. We want the actual event to be all tails. There's only one way we get all tails. It's tails, tails, tails. which means that this is 1 out of 8. If you write that as a decimal, it'd be 0.125, which is 12.5%. So in other words, what we're saying is the chance that you flip 3 fair coins and you get all tails is only 1 out of 8, which is only 12.5%. All right, so again, notice that it's very nice when our sample space is sort of written out as sort of in its most basic form. But you can imagine, even with only three coins, the sample space is starting to get really sort of unwieldy, right? We sort of saw that one coin has got 2 things, 2 coins has got 4, 3 has got 8. If we did 4 coins, there would be 16. If we did 5 coins, there'd be 32. And we'd have this crazy chart of all these messy sort of H, 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 T, H, H, T, T, H, T. It would get very sort of hasslesome. So while it's nice when you can write out this whole sample space, it's pretty rare, and we'll sort of see that as we go further into our study of probability, we'll be doing this less and less. Because as things get more complicated, you really don't want to have to write out the entire sample space. But again, right now we're just starting off the basics, so we're trying to build everything from the sort of ground up. All right, let's look at one more sort of basic example and then get into another set of important definitions here. So let's go ahead and take as this example here. Let's suppose you have 7 people in a room. So you got these 7 people. The first person is Aaron, who is male and age 20. Then there's Bob, who's male and age 30. Then there's Cindy, female, age 20. Dave, male, age 40. Emma, female, age 30. Frank, male, age 50. And Gina, female, age 40. So you pick one person at random. What we're going to do is we're going to start by writing out this sample space in 3 different ways and sort of talking about how some of these different ways are maybe less or sort of more useful. So let's do that, and then we're going to calculate some probabilities. So what's probably the most useful sample space? Well, the most useful sample space is sort of treating everybody as their most basic. So the most useful sort of sample space is to say that the options are you either choose Aaron, Bob, Cindy, Dave, Emma, Frank, Gina, right? That is the most basic sample space. It says if you're going to pick somebody from this room, well, these are the 7 people you could pick. But we said that there are some different ways to write out the sample space. Well, notice we could also say that the sample space is that there's really only 2 outcomes. You either get a male or a female, right? When you choose somebody from this room, you either end up with a male or a female. We can also say that the sample space is that you get somebody who's age 20, somebody who's age 30, somebody who's age 40, or somebody who's age 50. Now, the reason I'm sort of showing you guys that all of these are valid ways of thinking about the sample space is that these 2, however, have that sort of limitation. These 2, the outcomes are not equally likely. There's sort of an issue with the outcomes here, right? Because even though there's, male and female, the chance that you get a male is not the same as the chance you get a female. Because if you think about it, there's more males, 1, 2, 3, and 4, than there are females. Same thing with the ages, right? Age 20, 30, and 40 all are sort of equally likely, but age 50, there's only one person who would satisfy that. So while these are fine ways of sort of describing the sample space, they don't have that property that the outcomes are equally likely. So we have to be a little bit concerned about using them. When we think about this, we sort of want to think about the most basic aspect, which is that there are 7 different people there, and those are all equally likely. All right, let's calculate some probabilities here. Let's get the probability that we choose Aaron. Well, if we do this, we can think about this as a fraction. If we do this, we're not going to use these here. We're going to be using this one here. There's 7 different outcomes, and Aaron, of course, is 1 out of those 7. So we can say that the probability is 1 out of 7. Again, if you want, you can write it as a decimal or percentage, but we'll just leave this one as a fraction here. Okay, what else can we calculate? Let's calculate the probability that we get a female. Again, you might be tempted to say, okay, let's use this one and call it 1 out of 2. But again, we know we can't use that because they're not equally likely. So instead, we look here and we say, okay, it's a fraction. It's going to be out of 7. How many of these outcomes satisfy that we chose a female? Well, Cindy, Emma, and Gina all do that. So we get 3 out of 7. Finally, if we want to do the probability that we get somebody who is age 40, then that's also going to be out of 7 because there's 7 people in that room. What is the sort of age 40 people that will sort of satisfy what we want? Well, we know Dave is age 40 and we know Gina is age 40. So we would get 2 out of 7 there. So, in other words, notice that to calculate all these different probabilities, we're sort of using that most basic representation of the sample space. Now, I do want to just make a quick note with this. So I'm just going to sort of divide this off. It wasn't part of the problem, but let's just make a note here. Note, if we did look at these sort of sample spaces here, we could have sort of made a little list, right? We could have said outcome on like the first one, like male and female. And we could have just recorded what those probabilities were. For male and female, right, we know that the probability for male would have been 4 out of 7. And for female, it would have been 3 out of 7. And then, even though these weren't equally likely, we would have had the information we needed for this sample space, right? If we were only interested in gender, then we might want to sort of not really think about all 7 of them being there. We just sort of say that males were 4 out of 7, females were 3 out of 7. If we wanted to sort of look at the other one, right, about age, we could have said, okay, the outcome is age 20, age 30, age 40, and age 50. And then the probabilities associated with those, well, they wouldn't all be equally likely. Age 20 would be 2 out of 7, 2 out of 7, 2 out of 7, and age 50 would be 1 out of 7. Because remember, there was only one person who was age 50. It was that guy Frank there. Now, the reason I'm calling you guys' attention to these is because these, then, even though the outcomes are not all equally likely, they give us all the information we need. If we were only interested in gender, we knew that there were only 2 gender options, and here were the probabilities associated with those. If we were only interested in age, we knew that there were 4 age options, but they weren't all equally likely. Instead, they followed these probabilities. This type of thing here that shows you the outcomes, even if they're not equally likely, and their probabilities, gets a very special name. We call that a probability model. So in our next slide here, we're going to go ahead and take a look at the definition of a probability model. So let's go ahead and do that. So a probability model is a list of all possible outcomes of a probability experiment along with their associated probabilities. A probability model always follows 2 major rules. So the first one is that the probability of any event is always between 0 and 1. Mathematically, that means that whenever you calculate a probability, you're always finding a number between 0 and 1. You'll never get a probability that is negative, and you will never get a probability that is like 2. It's always going to be between 0 and 1. If you ever calculate a probability and you actually get a number like 0, we should probably realize that that means that that event is impossible, right? So getting a probability of exactly 0 means something is impossible. It's not the event is impossible. And if you ever get a probability like 1, what that means is that the event is guaranteed, right? So whenever these are sort of the spectrum for probabilities, right? The lowest a probability can be is 0, which means that it is impossible to have that event happen. The highest the probability can be is 1, which means that the event is guaranteed to happen. It will always happen. All right, let's talk about the second rule. The second rule says the sum of the probabilities of all distinct outcomes will be exactly 1. So in a little bit of notation, again, not necessary to have this notation, but we can actually use a summation. So if we add up over the outcomes, the probability of the outcome, then we will get exactly 1. And again, if you haven't seen a lot of summation notation, don't worry so much about this. Just know that the probabilities have to always sum up to exactly 1. Now, this is what a probability model is. Let's go back and look. We sort of built 2 things that I claimed were going to be probability models. Let's actually see if that was actually the case. So if we go back on this sort of page here, right, let's take a look at this first one here. Is this really a probability model? Well, are the probabilities between 0 and 1? 4 out of 7 and 3 out of 7? Definitely between 0 and 1. Do these probabilities add up to 1? Well, 4 out of 7 plus 3 out of 7, that's going to be 7 out of 7, which is exactly 1. So this guy is a probability model. What about this guy here? Well, are these probabilities between 0 and 1? 2 out of 7, 2 out of 7, 2 out of 7, 1 out of 7? Those are all greater than 0 but less than 1. So we're good on the first condition. And if we add them up, 2 out of 7 plus 2 out of 7, that's 4 out of 7. Plus 2 out of 7 again is 6 out of 7. Plus 1 out of 7, that's 7 out of 7. That is 1. So this guy is a probability model. So these things here that we just were sort of creating, these are examples of probability models. Okay. In our next video, we'll take a look at some more examples of looking at probability experiments and building probability models for them.